go ahead. Yeah. Okay, Stephen. Yeah, let's wait. Yeah, it's still early, so don't start yet. Any questions before we go on? I posted the instructions for the assignment 5 and 6, and we talked about them on Tuesday. For those of you who missed it, let me know if there are any questions. So next week we'll have two extraction is the optical design or photonic design for extracting light out of substrates for LEDs and so on. So this is, of course, of great importance to displays and your phone display or your laptops, whatever. Then the second lecture is on light trapping, of course, which we have already talked about, but James will talk in a little more detail because it was part of his PhD thesis on light trapping for solar cells, photovoltaics. And then the week of the following week, we'll have, that's the third last week, so we'll have a lecture and a really interesting set of guest lectures from the industry. So I'll make more announcements as we go along, but make sure you attend those. Okay, are there any questions before we jump in? So today's assignment 4, I hope everyone's ready. And okay, so as same as before, you have about 10 minutes and then about less than 5 minutes for additional questions and discussion. Okay, people are still coming in, so let's give it a, I think almost everyone's here. Okay, Stephen, I think you can start.
Okay. So we are the Pure Water Vision team, and we'll be going
Go ahead.
into a more.
Floor's yours.
We'll be going to a more analysis on our water pasteurization device. So in this analysis, we'll be going over the simulation of a solar cooker and how it works in our flow-through device. We'll be going over the model of our water pasteurization. We'll go through each component, look at the dimensions and the basic functions of each part, and we'll be looking at the cost benefit of implementing a parallelization part at the beginning of the flow-through device by preheating the device and filtering the device at the same time. And we'll be comparing how this device compares to other water pasteurization devices. So I'll be giving it up to Carl to talk about the simulation of the solar cooker part of our flow-through water pasteurization device.
Yep, thank you. So we ran an optical simulation in COMSOL. So from these two images, you can see the red arrows. Those are going to be the solar radiation direction. So the solar radiation is coming from about an ideal position in these models, but you can see that the intensity varies with the angle of direction, and it also varies with the refraction through the glass pane, which Stephen is pointing to right now. So the light comes down, reflects at a 60-degree angle, and then hits that base plate. So our next image, the next slide, sorry. This next slide is going to be how many of those rays hit the base plate. So we ran a simulation to basically trap all rays that hit the base plate. And you can see that we have a pretty uniform density of the intensity. So this is really good for us because what we want is a very uniform spread, because we're putting a bucket in this and we're also putting tubing in this. So we don't want a very concentrated light beam that could potentially melt our plastic or materials. So we can see there's a couple of spots where it's red, but even that, it's not going to be enough to cause any damages to our system. So the next thing is how much is really collected. So ideally, the sun emits about 1,000 watts per meter squared. The solar cooker area is about 1.115 meters squared. We measured in inches, it's about 2 by 2 feet. And then the ideal power from this system, with ideally, if everything reflects, there's perfect reflection, and everything hits the base plate, we get about 1,115 watts, but that's not realistic for a model. As you can see from the image on the right, the sun angle plays a huge factor in how efficient our system is. This image over here is simulating a similar latitude to us in New York. So you can see that the angle of this one is much less ideal than the other image, and the intensity is much less. So the non-ideal absorption is also a factor because we're using a black cloth to absorb the rays that enter the box. The non-ideal reflection is a factor. It'll be aluminum foil, so not everything gets reflected ideally. So the total efficiency, unfortunately, for an average day is about around 10%, which is still pretty good and will get us quite a bit of water per day. But yeah, the realistic average power output is closer to about 50 to 100 watts.
So now I'll be handing it off to Abdullah to talk about each component of the device.
You hear me?
Yes.
Yes, go ahead.
Okay. For the device modeling, this is the 3D drawing to show the flow through device component composition, starting solar cock, heat exchange, main solar cock, water receiver, proposed embarkment, pasteurization of starting solar cock, filtering and preheating water. And for the starting cooking solar cock, the solar cock here is showing the solar cock, the normal box solar cock, and the body for it, it's 24 inch time 24 inch and time 24 inch. Panel dimension and 24 inch, also time the 24 inch time 0.5 inch. Barrel, the container gas goes inside box cooker. For filter, Sherrill filter and filter dimension, also 24 inch time 24 inch times 3 inch. Pasteurization, preheat water for 20 column to 28 column and save around 48 minutes to pasteurize complementary.
Abdullah, could you go back and explain to me where are the different parts, the solar cooker, filter, and parallelization? Like, where's the solar cooker in this picture?
It's like this. So this picture doesn't really model the solar cooker too well. This right here is supposed to be the solar cooker part, and these rings around here are basically the different filters that the water will go through.
Yeah.
And the flow through is happening
Yes.
over the perimeter, like in a circle, like tubes?
Yes, it will
Yeah.
flow through the tubes.
Okay, go ahead. Yeah.
And for the heat exchange dimension, the 6-inch time 4-inch time 2-inch uses heat for pasteurized water to preheat the cold water coming into the main cooker, greatly increases efficiency. Water distribution for starting solar cook to main solar cook to water receiver. For main solar cook, the main solar cook here, normal solar box cooker, coiled black tubal, carries water through for the heating, heats water to 70 column for pasteurization, contains thermostat valve, resolve reloads water when proper temperature is reached. Dimensions 24-inch and time 24-inch time 6.5-inch.
Quick
Panels
question.
dimension
Sorry, Abdullah. Quick question. In the previous slide, the panel that you showed, is that sitting underneath the solar cooker? Are they two separate items? Yeah,
These are
this one.
two separate items. So
Okay.
if we go back here, this is the heat
Correct.
exchanger, and this is supposedly the main solar cooker, but we designed it to be like a more to scale for this image.
Got it. Okay, go ahead.
and here for the water receiver hold a dimensioned pasteurized water, dimensions 24 feet time 24 feet and time 24 feet here.
That's supposed to be inches. Okay, so
bad.
next we'll be going through the cost analysis of the flow through device. So here I made bills of material to make this flow through device. So this may not be the cheapest, but it's pretty close to that. And from looking at this, what's different about this than a normal flow through device is that we have an extra solar box cooker at the very beginning. And what stands out to me the most is how 20% of the cost is mainly from the heat exchanger. And if we were trying to market this to a poverty-stricken area, that's probably not a good idea. And we can probably take the heat exchanger out, which is not needed for the functionality of it, but more for like the efficiency part of it. Or maybe we can market to other people, such as people who are going camping for long periods of time, or to people who live in rural areas.
Yeah, that's a great insight, by the way. And some of that decision making will come from the canvas. So I will be interested to see how that is reflected in the canvas that you submit. But go ahead. Yeah.
So this is a cost analysis of various different water pasteurizer from paper, and it shows a water pasteurizer using heat, flame heat, a solar cooker, flow through device, and 2 different solar puddles. And we'll be trying to emulate this for our device to compare it with these. So first, there's really no maintenance needed for this flow through device other than replacing parts that are broken or replacing parts that degraded over time. One thing that needs to be changed is the filter, which probably needs to be changed on a yearly basis. So I took this into account with having to change the filter, which cost about $5 per year, into this calculation here to calculate how much more cost efficient is our proposed flow through device compared to the original flow through device. So doing this calculation, I get that the cost efficiency is improved by 1.9% each day And over a year, this cost efficiency compounds and goes to 704% in a year. So
when you say percent increase, you're comparing it to which example in the previous slide?
This original flow through device.
I see. Okay, got it. By the way, you have 2 minutes, so try to hurry.
Then I tried to replicate what was in this paper, which measured in liters of waters per dollar over long terms, which is 5 years. So I did the same thing, and for this water pasteurizer, you can make about 21 liters of water per day, but for our proposed water pasteurizer, we can produce about 26 liters of water per day. And accounting for the maintenance and the cost of this water pasteurizer, the liters of water per dollars is about 616, which is a bit more than the original flow-through device, but it compared to a solar puddle, it's still pretty lacking behind. But compared to a solar puddle, this flow-through device is much more compact and can be mobilized to other locations, unlike a solar puddle. And that's the conclusion of our presentation. Any questions?
Great. Yeah, that was really good. So I did have a couple of questions on the first of all, the cost modeling is very nice, and it's good to see that you actually compared to existing solutions, and this also gives you some guidance as to where your potential customer segment could be, the impact of portability and compactness and so on. So Carl, can you go back to your simulations and explain? Yeah, maybe this slide. Could you go through this a little more detail again? For instance, what is the difference between the left-hand side and the right-hand side? What's the difference between the red rays and the blue rays?
Sure. Yeah. So on the left-hand side versus the right-hand side, it's basically just two different views of the same exact model and simulation. Because there was, in COMSOL, you can do like an orthogonal, but it was impossible to see like anything. So I did a X and Y, I think, and a YZ. So the different rays here, you can kind of see the light blue versus red versus blue. There's a little legend over there. So COMSOL kind of gave us a little legend of like, if the rays were lined up, so like the red rays are in the same orientation as the initial sunlight. It's like the red arrows come in this way and the red rays are also that direction. So it looks like COMSOL said that was a higher intensity because it was reflecting kind of almost with the sun. And then if you can kind of see below, it turns to orange. So like through the panel. So the rays come down and they come through our glass panel and they turn orange. So that has to do with the refraction and dissipation of the light.
There's some Fresnel reflection losses,
yep.
I assume.
Yep.
Okay, I see. Okay. And when you said the optical efficiency was 10%, can you explain exactly how you calculated it or estimated it?
Yeah, so this was a bit more tricky because it was not really that easy to do like a day-long simulation, I guess. So it was almost more of an estimation of kind of like the losses and the idealizations. So if you can kind of see from the image on the right, this is almost the exact same time of year, but just in a different location. And the sun angle is completely different. So if you just if you leave a box sitting there, we kind of calculated like the average that came in.
Okay. Got it. Okay. I think that's reasonable. You probably want to do this for Salt Lake and
the one on the right is New York because Salt Lake wasn't an option, but it's a similar latitude. It's like 40 versus 41.
Or Arizona or something. So
yeah. So we did the first one was in Caracas, Venezuela, so it's closer to the equator. Okay. But then we did one that was not idealized, and that was the one. That's that one right there.
Okay, got it. Okay, great. That was very good. Okay, let's have the next team, the daylighting team. Who wants to share?
I'll be sharing.
I'm not sure who spoke, but
Oh, it's Dan. Sorry.
okay, Dan, go ahead. Sorry, when I'm on, for some reason it doesn't show me the.
Oh, the name.
Yeah, go ahead. Yeah.
I'm going to start talking.
Okay, Wei, you're on. Yeah.
Okay. My group is designing an adjustable window shelf device for the daylighting project. So my team name is Shining Light, and my team members are Daniel, Austin, Skyson, and me. So next page, yeah, the content, we are going to cover 4 parts for the presentation: 3D modeling, light shining simulation, sound tracking system design, and the initial cost benefit analysis. So 3D modeling, I'm going to talk about the 3D modeling part. So as indicated by the top left pictures, so the sun changes its position throughout the seasons, and also the position varies during the day. So if we just have regular windows, the sunlight can penetrate the window into the room. But how to distribute the sunlight more evenly inside the room? So we come up to use a shelf device, and the shelf device can be driven by 2 motors. So it can move up and down, and also it can rotate itself. So we put a photo sensor on the shelf to track the sun. So the shelf can adjust itself accordingly. So, and also we are going to use a solar panel to power the device. So we don't need to pay the electricity cost. And so we pick up like a double hung window because this window can move, can be open like up and down, both top one and bottom one. So it won't open outward to interference the device. And the bedroom dimension we use is 4 meters length, 3 meters width, and we pick up the standard height 2.7 meters. So this one is the 3D modeling of the device. So we can see from the picture, so the left one, the blue one, is the solar panel to power the device. And the top middle one, it is a linear real guide device and a needle screw. And the motor, once the motor rotates, it passes the torque to the needle screw. So the needle screw can rotate. And there is a sliding block on the needle screw. So the sliding block can move up and down when the needle screw rotates. Also, there is another motor as indicated by the bottom right picture. There is another motor on the slider blocks. So once this motor rotates, the shelf device can be tilted at any angle we want. And the next one. So these are different.
So just wait, sorry, just to be clear. So you have 2 axis motor, 2 separate axis motors here. One to twist
one is on
and
the
one
top
to
and
translate.
one is on the slider. Yeah.
Interesting. Okay, but both are powered by the same solar cell. So you have some panel, sorry, and you have some control that you're going to talk about, I assume.
Yes, that will be the third part. Yeah.
Okay, go ahead.
And so these are the different scenarios of the device. So from the top 3 pictures we can see, so the windows can be open, like up and down, like in plane. So we can have like a fresh air inside. And you see the shelf device can be moved up and down in different positions. And from the bottom 3 pictures, we can see it can be tilted at any angle we want. It can be perpendicular to the window, and it can also be horizontal to the window. It depends on the photosensor detection. So my teammates will talk about the following parts.
All right, so I did some simulations in a program called AGI. That's sort of like a construction lighting simulation software suite. So there are two things that actually kind of factor into the benefits portion that I was looking at. The two benefits as far as lighting goes with these devices are you get a reduction in glare close to the window, and you simultaneously will get a better dispersal of light throughout any given space. I wasn't going to spend any time really talking about just normal static light shelves and the benefits of those, because those have already been shown and already been proven. So my goal here is to kind of go over some of the benefits of being able to have this sort of modular or adjustable type of shelf unit instead. So the first simulation I set up, all I wanted to do was demonstrate how different heights and angles can affect the glare in any given space. So this was modeled in mid-morning. So if you're, looking at the sky, it's about 45 degrees from the horizon that the sun is. And at this point, in order to get the maximum light within a space, you would want the shelf to pretty much just be flat. So what I did was I showed that with the flat orientation, the orientation that you would want for a longer dispersal of light anyway, you'll actually see in these lighting calculations on the left that there is a huge reduction in comparison to the below image as far as the light levels adjacent to the window. In the lower image, the one where it is tilted, we're seeing, oh, and by the way, I apologize, I forgot to label it. The units on here are foot candles. But we're seeing adjacent to the window, we're getting 9.4 foot candles. We're getting a huge number in comparison to what we're getting above, where it's dropping down to more comfortable levels. Go ahead.
Dan, quick question. So the top row, the left and right are correlated. So am I looking at it? Are these two the same?
Yes, that's correct. That's correct.
Okay.
I have one question. Yeah, sorry.
Okay. Yeah, go ahead.
So how was this simulation done? Like in what software? And
so the software is called AGI. It's a software that I was just more familiar with, so it allowed me to do a lot of modeling of different kinds of spaces very quickly. So that's what I opted to use.
Yeah, it's very nice. Yeah.
But I personally like it. Yeah, one of the things I like about it is that it does let you render things. So you can kind of get more of a view of what an actual space would look like.
But I'm actually not familiar with this, but it looks very nice. So did you say the name was again?
AGI, and to be entirely honest, I am not even sure what it stands for.
Oh, okay.
But it's a software that I just use at the office.
Oh, what is this? What are these things right there?
So all of these are the calculation points. Each one, they're spaced. In this one, they're spaced 3 feet apart, and they're just giving a foot candle calculation at that point.
And what is this?
That is an object that actually no longer needs to be there. I was initially modeling with just light fixtures while I was in the process of figuring out how to model sunlight more correctly. So those are fixtures that have been disabled, but I just had forgotten to remove them from the model. This black line that you'll see actually between the two spaces is just a tall wall I created because I didn't want light interfering, because both of these were running simultaneously. I didn't want lights, from either one somehow affecting the other. Okay, so
go ahead. Yeah.
For the next one, we're just looking at the model of just a simple small residential room. Please pardon the strange looking human figure. That's just what was in the object library. So this one is modeled at noon. So typically on this one, if you're wanting to reflect light further into a space, you're going to want to have the light shelf angled in such a way that the reflecting edge of it is pointed towards the space, right? So this is if you were just using a flat static light shelf as you commonly see. If you look on the left-hand side, on the left image, on the left-hand side, the numbers 3.7, 3.9, 3.7. We're seeing these foot candle levels. And then with a slight adjustment, you'll see that we get up to, we get 0.2 or 0.3 increase in foot candles. And this was also just done, not even necessarily, I didn't even think about optimizing the angle and height perfectly. This was just eyeballing it. So I liked doing it this way because it's a demonstration of how you do get a benefit from angling even without the optimization that comes from the sensor system that Sky is going to be talking about. Also to clarify, I did model the light calculations. If you look in the right image, you'll see how the text is floating. I modeled them at about 3 feet because that's what's called the work plane. That's where desks and tables, things like that typically are. So a lot of the time when you're shooting for a certain light level, you want to make sure you're hitting that light level at the work plane. There are some areas where you want to make sure the ground is lit a certain amount, but a lot of lighting requirements specify specifically what they want in the work plane. So
when you say you eyeballed it, did you look at those foot candle numbers and try to maximize this? What you mean?
No, in fact, I actually got better, slightly better numbers when I made it, because if you look at the angle of the shelf on the right hand image, it's about 30 degrees or so. You'll actually get a better light distribution if you're doing something closer to 40 to 45 degrees. But what I wanted to show with this one is that even without optimizing it, we have not the optimal angle. We have not an optimal ceiling situation because we have a ceiling fan, which is further redirecting the light in other directions that we may not necessarily want. So this was, and I apologize, I should have explained that a little better at the beginning, but my goal here was to demonstrate that the ability to rotate in and of itself provides a huge benefit. Once it is optimized further, then you get even more benefits on top of that.
Okay, yeah, go ahead, yeah.
So Sky will take over for this portion here.
Hi, can you guys hear me?
Yes, go ahead.
Okay, hi, here's this Sky sound. The part I designed for our project is the sound tracking system. And that is just because we need it, not because my name is sound. So this system is based on the Arduino, and we can see the two step motors at the top, and each of them is controlled by a chip which connect to the Arduino, and the whole system will be provided the power from the solar panel we choose, and the calculation will be shown later. In our system, we have at least four, but if we want, we can add some more LDRs into the whole system. And some of them will be placing outside of the window or the panel, like the edge of the panel, to collect the data from the sunlight, which is like how many power we can generate from the sun, and the rest of them will be set in the room and where the place we want the more daylighting going in to make people feel better in the room. So even I put 4 LDRs in the breadboard, but in fact they're separately, and if we add more, we can put it everywhere. Like by my design, it can also like some of them in the window edge and some of them on the edge of the panel, so we can calculate how many efficiency we get from the power and automatically correct the direction of the shelf face to the sun. Next slide, please. And because we don't have any battery in the system, we can lower the cost, and we don't want to use like the room energy, so we trying to choose the better solar panel to provide energy for the whole system, include the two motors, the LDRs, and the Arduino itself. And by the calculation, totally we need like 8.3 watts. Considering about the energy loss and any trans loss, we choose a 15 watt solar panel. And we all know, I think we all know, the Arduino is be powered by 5 volts or 12 volts. So I think 5 volt is good enough. So the solar panel is be chosen to 9 volt 50 watt. And if the whole system is larger than we expect, we can choose a higher power supplied solar panel to our system.
All right, so I'll go over some of our cost analysis here. There are a couple things we were able to save on. Like Sky said, we don't need a battery pack, which is nice because I mean, if we're not getting enough light to power it through the solar panel, we don't really need to be, putting a lot of effort into utilizing a light shelf anyway. So this is just the some of the parts costs that we found. As far as shipping, installation fee, shipping, of course, is going to vary based on any location from manufacturer to where the installation is occurring. For installation, though, because it just needs to be mounted externally, we just estimated that at about $50. It pretty much would need to be screwed in to where we're using it, and that's generally all that needs to be done. So we found the total for the device with a 1 meter panel would be around $300. Now, we also wanted to look at some of the benefits and some of the sort of reasoning that people would opt to use this kind of system. First one that we talked about in more depth in one of our earlier presentations was the fact that a natural lighting is just better for human physiology and psychology. People are more comfortable, more productive, even have better moods when there is natural lighting in a space. So it definitely helps with that. The other thing is that you can have energy savings, of course. So the example I used was if we had a row of these shelves installed along the side of an office area, and it was reflecting enough light that we could have a row of 10 troffers, these 2x4 lights you typically see in like grid ceilings and things like that. But if we were reflecting enough light that we didn't have to have 10 troffers in this space on, that would be $151 per year, and that would just compound every year. And this was done using what is already a very energy efficient troffer. So if you have a space that is using old fluorescent troffers, with fluorescent tubes in them, you'll be seeing savings that are 3 to 4 times this much. If you have a space that's being lit incandescently, like a residential space, like some of those simulations we showed earlier, which very commonly use incandescent bulbs that are very energy hungry, you can see massive savings. The wattage of one of these troffers that I modeled is 38 watts, and the wattage of the bulb currently lighting the bedroom I'm sitting in is 40 watts. So it varies greatly depending on the type of space that this is going to be implemented in, but going in order from LED to fluorescent to incandescent, you're going to get the least to the most energy saving. So
how did you come up with the 10 troffers? Are you trying to match the illumination, the brightness?
So yeah, I just did this as, honestly, it was a bit difficult to.
Yeah, it's not an easy problem. Yeah.
It was kind of honestly just an assumption. It was just hypothetically, if we had a space where we could throw light enough that 10 troffers wouldn't have to be on. And
Got
it
it.
had to kind of be arbitrary, unfortunately, because the energy savings that you'll see with this device varies heavily depending on the application location, you know, where this is
Yeah,
going to
yeah.
be, what the
So-
existing lighting is, you know.
Yeah, you're almost out of time, but this is really good. I have one suggestion is you may want to pick one particular application or one particular installation and try to figure out quantitatively what it could be. And you can make a guess as to what your best situation is. I agree completely that this will be very dependent upon how it's applied and how it's used. The other thing you could do is look at companies that do daylight redirecting films like 3M or architectural firms and try to contact them and get a sense for or look up their literature.
That would be to be honest, some of the initial numbers that I had run I found to be incorrect, so I had to remake this slide with a little bit less time than I would have liked. So that will definitely be something that I will be addressing in much more detail in future.
I'd be very curious to know. This is a very important comparison. So I'm very interested in understanding this better. But I'd say, could you try to wrap it up in a minute or two?
Oh, well, with that being said, I mean, all that's left is questions. So yeah, we're good. We're good to go.
Time. Yeah, this is fantastic. So I would say, are there any questions I forgot? I meant to let the other students, if anyone has questions, feel free to jump in. Okay, if not, let's move on to the next team.
All right. Thank you for your time.
Thank you, delighting team. This is very, very interesting. And I'm actually quite interested in understanding your canvas too. Actually, everybody's canvas, but every canvas is a little bit different and you will have different insights. So this is actually quite important. And by the way, after you submit the canvas on the last assignment, one of the things that I'd like you to do is to highlight what you learned from going from initial to final. So just remember to do that as well. Okay, Solar Shade team, you're on. Go ahead.
Hello everyone. This is Team Solar Shade. The team members in our team are Fro, Tara, and me, Nick, and me, Yo-Yo. Our design name is called Solar Shade, and here is a design drawing of Solar Shade, which is basically a bifacial solar awning that is a combination of both a solar panel and also a awning underneath it. And here's a breakdown of our design. So our solar panel has a electrowetting layer on top of the solar panel part, which helps track sunlight. And our solar panel part has bifacial solar cell and HPC film. Underneath our solar panel, there is a awning which acts like a white background that reflects useful wavelength. We can also add optional thermal harvester to help absorb excess infrared wavelength and turn its thermal energy into electric energy. Besides that, we incorporate our awning with a origami folding technology.
Quick question. Why do you have the HPC film there? And what is that?
Oh, so HPC film can help leak through the unwanted lights, for example, infrared lights. And so the solar panel can just absorb the wanted wavelength. And the unwanted infrared lights can heat up panel, which can, cause damage to the panel and lower its efficiency.
I see. But
yeah, and the awning underneath that so the optional thermal harvester can absorb that infrared lights, So
why wouldn't you make a multi-layered film like the purple and the green on top of each other, as opposed to interspersed? I didn't understand why you chose
Yes.
this architecture.
So the electrowetting layer is kind of complex. First, it tracks the sun when the angle of the light changes. The structure of the water droplet will change.
I see. Okay.
Which Tara gonna introduce more, like explain it more later. And
Okay,
by
got it.
doing that, the sunlight can focus on like a smaller area, whereas the purple area and the green area will mostly not have much light. So it saves our material fee by reducing solar material. And HPC film is really cheap. I mean, it's cheaper than by
I'll be talking
understood.
more about it, Dr. Menon.
Yeah. Go ahead. Yeah, understood.
Oh, and I'm just gonna finish the origami folding. By adding fine creases in between materials, we can let the awning, we can roll the awning up during dangerous weather conditions and protect the material inside. And so, yeah.
So I'll be talking more about the bifacial solar array with holographic planar concentrators. And so you asked us why we decided to have them, instead of multi-layer, we have them side by side. So the reason for that is that since these are bifacial cells, they can collect light from both the top and the bottom. And so by utilizing strips of HPCs, then we're able to bounce light not only back to the front, but also to the bottom of the solar cell, and therefore harvest additional electricity. HPC is, the benefits of it is that it's a selective wavelength concentrator. And so it only reflects lights that can be used by the solar cell. It also does infrared light filtering. So any infrared wavelengths will pass through and not affect the solar cell. And it's static, so there's no moving parts. As well as bifacial, since we're so then we have the ability to harvest from more energy from all the light from HPC, as well as I'll talk more about it, but using half the solar materials needed to achieve equal power output compared to monophase, as well as HPC can take an incident light and diffract it into a bigger range. And so without the actual product, it's a little hard to simulate. There's not a lot of simulations out there, but without the actual product, it's hard to gather data. So through a lot of research papers that I've read that other people who've built this and tested it, as you can see here in the top left, we have a diagram showing a incident angle where you have your HPC here. And they're saying that from their testing, an incident angle of 0 degrees or 10 degrees can essentially give out a diffraction range of 30 to 40 degrees. And so no matter where the light is and how small or big the incident angle is, the HPC is able to diffract that light and allow the solar cell to harvest more energy. As well as mentioned before, it allows infrared wavelengths to pass through, which can't be used by the solar cell and just increases the temperature of the solar cell, and then causing it to be less efficient and not optimal. And so here in the bottom, we have a solar cell by itself. As you see, it gets quite hot. And then with some thin film HPCs in between, the solar cells get cooler. And then with additional more HPC film, then the solar cells even get more cooler and can run at its optimal operating temperature. And then,
So in this simulation, is there a concentrator used, or is this just direct sunlight? No concentration.
So there is a concentrator used in between these yellow lines. So the yellow bars are the solar cells, and then the blue bars are the HPC film.
Yes, but is there like a CPC or a lens or something like, or mirror or something like that on top? Is there an extra? Okay, so this is just direct incident sunlight on this system.
Correct.
Okay,
and
very
then
good.
Per Kostuk's et al.'s paper, he and his team built a bifacial with HPC module and wanted to compare it to a monofacial module. And however, they found that comparing module to module would be wouldn't provide any benefits, or it would be very hard to compare due to how the full sun conditions is different for each module, the setup of each module, and the temperature efficiency of each module. And so his team found a more effective way to compare these two would be the energy yield per gram of silicon. And so for a solar panel or module of thickness 240 micrometers, they found in their testing that a bifacial with HPC module needs only 3 grams of silicon per watt versus a PV cell module that needed 8 grams of silicon per watt. And so concluding that approximately with the bifacial and HPC module, we can use approximately 50% less silicon to generate the same amount of power as a monophase. And so this is what I found. And with these findings, it seems that HPC is very good to use and offers a lot of benefits, as well as it's cheap compared to any solar cell material. And so here's
sorry, quick question. This is by the way, very nice analysis. Is there a way to tie? And I don't know if Ray Kosuk did this. Tie this grams per watt to actually dollars per watt, including any cost, the balance of system.
Yeah, so for as dollars per watt, that got a little tricky due to when researching about these individual cell modules, there's not a lot of information about its pricing. When you order a solar panel, you usually do it through a company where they can do mass productions, and so they can get the cost down.
Okay, yeah. So that would be an important point to find out if possible. But it's okay. Yeah, if you don't have it, it's fine. I understand it's not because these things are not commercially available, I assume. So go ahead.
And then here's Tara to talk about the electrowetting layer.
So solar shade is new and exciting since we're going to be able to take advantage of electrowetting, which is basically the modification of the wetting properties of a surface with an applied electric field. So we are obviously limited to like the physics of water's surface tension. So when we were designing our water droplet shape and size, we had to keep this as a design consideration. So it had to be about 4 or 5 millimeters in diameter to be able to keep its droplet shape. If we hit the next slide, we can see that our solar shade.
Quick question about the previous slide. Is this sorry? Is this an electrode?
Yeah, so that's a electrode. Yes.
Okay. And how did you? And you're saying you picked this 5 millimeters such that you could maintain the droplet shape. Now, remind me, is the liquid sandwiched between something else? Like, is there a cover glass kind of on top?
Yeah.
Like a flexible plastic on top.
And it's an air gap in between? So the
Yes.
liquid is just sitting in air. Okay, go ahead. Yeah.
Okay. So when we wanted to simulate this water droplet, we had to make various different shapes to figure out which one was going to work better. That's why we slowly got flatter on this. So we want to get the most optimal amount of sunlight rays bent towards the solar cell. So here we ended up actually picking that first rounded ellipsoid shape since it's working best for direct overhead sunlight. Our next slide, we actually moved the sun 20 degrees to the right from the vertical. And so we're able to see that the light rays are being steered towards the solar cell. So they're getting like slightly more concentrated, I guess, but any light rays that are not going to hit the solar cell in its entirety will still be able to get reflected back from the HPC film. So the next slide.
So sorry, I have a quick question here. Let me make sure I understand this analysis. So the left-hand side is essentially a squished version of the droplet on the right-hand side. Is that what you're saying? And that changes the focusing power of the lens. essentially?
So the right image is more ideal because it's bending the light better. That's why we picked the rounder shape compared to the flatter shape.
Where is the solar cell itself, the bifacial cell in this picture?
Underneath it.
Like in contact with it? Okay, I see. Okay, that makes sense. Go ahead.
And then the next slide, we just moved the sun 20 degrees to the left. And you can see our like droplet 3D model right there. So by changing the water droplet shape to match the sun's angle, we can basically just use this shape to our advantage to get.
Yeah, this is very, very cool, actually. So tell me a little bit about how realistic is it to control the shape in 2 dimensions like this? This is, by the way, a very cool idea. So is that realistic? Is that can you actually control the ellipticity in the, so here, for instance, you're changing the ellipticity in the X, Y plane and the Y, XZ plane and the YZ plane. So is that possible actually?
So I can speak upon that a little. So with the one electrode like here, it's more of where you can just kind of flatten and round the shape because the electricity will pull around this electrode. But if you want to have multiple axes like the one we're simulating here, then what happens is that you can introduce a second electrode on each side of the droplet, and that can act as a kind of a second axis to manipulate the meniscus even further.
Interesting. And is this, and I don't know the physics of electrowetting, but is it doing current injection or is it based on a potential, like a voltage?
It's based on a voltage potential.
Okay, so what might be really interesting is that could you use a solar cell itself? Because you have a PN junction there in the solar cell, right? It's
true,
a hypothetical question. You don't have to answer it, but maybe there's some really clever ways you can take advantage of the open circuit voltage of the solar cell itself to do this.
Yeah, that
but
would
anyway.
be very innovative and very interesting to look at also.
Okay, keep going, Tara. Sorry.
So if you want to hit the next slide, we just wanted to do a side-by-side to compare the solar cell light rays with and without the electrowetting. So you can see that on the left, the rays are not bending towards the solar cell, on the right it is. And when the rays do bend this way, it's going to save us, we aren't going to need as much PV material, so it's going to save us material, which is going to save our consumers money. And then if you want to hit the next slide, I'm going to turn the time over to Nick to talk about our cost benefit analysis.
Okay, so for the cost benefit analysis, basically we divided it into the monoface, which is like a normal solar panel, and our bifacial HPC at first, just to give a look at how they would be as like 2 normal panels. And the power production for each of them is about the same at 385 watts. The size of the panel is the same, 1.969 meters squared. And then because of, well, I guess just the normal price for the monoface is $1.50 per watt. And then for the bifacial with HPC, because we're using about half the amount of the solar cells, the manufacturing cost is about 70 cents per watt. And then with the electrowetting layer is 30 cents per watt. So that would be a total cost of $1 per watt.
This is really good. I had a quick question. How did you estimate the cost of the bifacial plus HPC?
Okay, so there was a paper actually on it in 2012 is when it came out, and that gave an estimation. And then
okay, great. Yeah. Perfect. Go ahead. Sorry.
Okay. Next slide, please. Thank you. So then with the total cost, basically, for the bifacial HPC, the size of the awning is bigger, obviously. So it's 4.459 meters squared. So then converting the 385 watts to the size of the awning would be about 900 watts for the whole awning. And then at $1 per watt, the solar aspect of it alone for manufacturing would be about $900. And then with the structure and install would be about $2,000 to $3,000 is what we would estimate. I would say about $400 for the rolling mechanism, and then the rest for the install. And then for the monoface, like a normal 6 kilowatt system is $17,700 about. And then converting that down to the size of 900 watts, it would be about $2,664 total.
How did you select the size of the system? Like I guess the size of the awning, because that's driven by some customer requirement, right? Like a house or whatever.
Yeah, like we looked up general size of awning. So this is like 8 feet by 6 feet. So
okay. So that's a kind of a standard in construction or something like that.
Yeah.
Okay, go ahead.
So that's it for the cost benefit analysis. And then for the thermal harvester, this is still optional. We haven't figured it out exactly, but basically the idea behind it is that they the rays that are not used that would not be absorbed by the solar cell would be absorbed by the awning and would not be reflected by the top of the awning. And then the bottom of the awning would still be cool. So then if you put the thermal harvester in between, then that would create then the difference in temperature could basically be converted to a difference in voltage, which is how the thermal harvester works, using the temperature differential. And then that would just be extra energy because it's not really being used anyway. So it would be better to use it with this, even though it's not super efficient.
Did you have some marginal cost on adding something like that on? And second follow-up question is, did you consider doing a modular design where you can retroactively add something like that as a premium or something? Go ahead.
That would be a good idea. We considered it at the moment optional. So we didn't really get into the details of making it modular, but I think that would be a good idea. And then what was the first question again?
Did you have a sense for how much more would it be to add something like this? And you have to make this cost benefit analysis, or is it worth actually adding this on? Or if I'm a customer, it's kind of like an add-on thing, I assume. So I have to think about that.
Right. I'm not sure exactly how much it would cost. It would definitely be, because of how much difference in energy it would be, it might not be super cost effective. But if someone
could I add on to that?
Yeah.
So there's been a lot of breakthroughs with thin film thermal harvester. So as far as any additional size or weight, it wouldn't be a issue, but they are quite expensive. And so I think part of what we were thinking for a benefit for the customer is, although this, the cost might be a little higher and you might get less, a little more wattage out of your system. One thing that we could highlight is that with these thermal harvesters, there is a cool plate side, and that cool plate side would be facing down towards anyone who's under the awning. So it would kind of create a more cooling effect for the customer. How much of a cooling effect, we are not sure yet, but that is something.
Yeah, this is actually what I was hinting to earlier. Also, if you had like a sandwich where this is sitting on top of the bifacial cell, maybe you can increase the lifetime of or performance or efficiency of the bifacial cell. I'm not sure.
Yeah,
but that's something.
That's also a thought too. Yeah.
Great. Go ahead. Yeah, I think you should try to wrap up.
And so in conclusion, by taking a look at our innovations, HPC, the bifacial with the bifacial cells, the electroweighting layer, as well as the thermal harvesters, well, we think solar shade, and then looking at the cost benefit analysis, we think that solar shade could be a good product that allows many customers who want to get into the solar panel game, but whether it be cost or aesthetics, this would also have dual purpose. So it shows very promising factors.
Yeah.
And so we'll open to questions now.
Great. That was very, very nice. I think in the interest of time, we need to move on to the next team. So thank you to the Solar Shade team. Well done. the desalination team. Who's okay, Joseph? Okay, why don't you go ahead?
Okay. Hey everyone, I'm Joseph Kiflam, and me, Prate, and Cedric make up the solar desalination team. And this is our in-depth technical innovation. So before we go into detail, let me just kind of remind everyone the motive behind our technology. So by 2025, approximately 1.8 billion people will have severe water scarcity. So our goal is to provide a sustainable, clean, and cheap source of water to a wide range of people and make it commercially applicable. Conventional desalination systems are energy intensive and they use 10,000 tons of oil each year. Brine discharge also threatens marine and biolife, and it's just kind of complex and expensive. So our proposed innovation, excuse me, I'm a little sick. Our proposed innovation of choice is solar still and a natural vacuum combination. So the operation principle behind this is fresh water vapors are produced from the saline water, which operate at low temperatures and low P because of the natural vacuum. So some advantages of this is wastewater and seawater can be reused. Our innovation is significantly lower in cost. Organic matter material can be prevented, and it can be integrated with large buildings, which makes it commercially appealing. Some disadvantages is the saline water must be maintained at a higher temperature than the fresh water, and it forms some non-condensable gases, but we do believe that it's something that can be maintained. So before we get into more detail, I'm going to hand it over to Prate so we can kind of go over the simulation and our expected results.
Joseph, a quick question. When you say non-condensable gases, what do you mean by that? I'm not familiar with this.
So there are just some like gases that are produced from the passive radiative cooler that can be harmful, but that is something that we should be able to like.
So it will be kind of inside that vacuum chamber. That's what you mean.
Mm-hmm.
And it's going to mess up the vacuum because it's basically going to reduce the vacuum.
It will like release the non-condensable gas like within the vacuum.
So you can have a valve.
Can I add on to that? So what happens is that there will be gases that diffuses through these columns as well as from the radiative cooler, and they will be here. And those are not water vapors, so they cannot be condensed. I mean, they can be condensed, but not, I mean, within the scope.
It's not useful.
It just can't be turned back into the.
Oh, okay. It's a good point. Yeah, I didn't think of that. Very, very good. Okay, go ahead.
So yeah, with that being said, I'll just hand it over to Prate so we can kind of go over our simulation and our expected results.
So as Joseph explained that it needs a big height of 10 meters and it's a cylindrical system, but what we are looking into right now is the evaporation of water, and the evaporation only occurs at the very top surface or near the top surfaces. So it kind of makes sense to, in terms of avoiding complexity, to model it in a rectangular geometry and having an axisymmetric symmetry. So what we did was that model it in a radius of 440 centimeter with a height of 10 centimeter. These dimensions are, I mean, comparable with what experimentally people uses. And the system is, I mean, the simulation I am talking about is like evaporation in vacuum, because the evaporation that occurs of the saline feed water is much lower pressure than what is atmospheric. Experimentally in natural vacuum, you can get 7 kilopascal, depending on like the system and everything. So to catch the evaporation, so what is modeled in like in two different terms. One is the heat sink. That happens because energy is being lost as the liquid from the system, as the liquid solvent changes into the vapor phases. So it gains energy, taking it out of the system. And there's a mass sink term that is associated with the loss of the solvent inside the cylinder itself, which of course then turns into the water vapors to the mass, basically remains same, but in terms of like solvent, there's a mass loss. So the evaporation rate is given by this equation, which is a typical physical equation of like evaporation under a vacuum system. It has got two important terms. One is the evaporation rate constant, It of course depends on the system and the atmosphere itself, but experimentally it's about 10 to the power 6 minus 6, and the other term is the difference between the vapor pressure, partial vapor pressure of the solvent and the system pressure itself. So the vapor pressure is basically derived by the Hamilton's equation, which is given by this, and the system pressure is what you choose into your vacuum system. And there exists as more and more liquid transfers into the vapor phases. So there's a loss of volume fraction in the liquid, which is basically simply with time respect to loss due to evaporation. And there also exists another physics going on, which is the transfer of heat, because there's a temperature difference between the outside and inside. As Joseph mentioned, that it has to be the saline feed water has to be at a higher temperature, so it's usually kept on the outside on the sun. So there's a temperature difference between the outer atmosphere and the inside, which basically at some point equilibrates. So if we go into the next slide. So yeah, so this is what in 2D symmetry.
Pratev, quick question. So what about loss mechanisms in your model? Is that something you have to consider? I'm thinking more like radiative losses or convective losses. Because I assume those are the two things, or I suppose convective losses can be very low because you could insulate it, but you still have.
So I have a thermal insulation. Everybody places a thermal insulation on top of it and around it, so to reduce the losses. But there's always going to be some losses, which I have not accounted into this simulation. For simplicity and complexity.
So. Just to make sure I understand this intuitively, so if I scale this whole thing up by by a huge amount, you in your model you will show basically a constant increase, a monotonic increase of production of water or evaporation, I suppose. But in reality, there's probably some saturation that will happen. That's my guess.
Yes. So if you increase the surface of the water where the evaporation is occurring, it would get increased amount of evaporation and increased amount of condensation. But in reality, there is always a boundary height, the moisture content comes into play and everything.
Yeah, got it. Yeah. Sorry, go ahead. Yeah, continue.
So this is what it looks like in a 2D thing, and if you as it is axisymmetrical, so it to convert into 3D like this. So the thermal insulation is on the top. The temperature difference between outside and inside, I have calculated is 20 to 60 because I know 60 is not the temperature that the sun gives. It's basically the inner chamber is made of a metal, preferably steel. So the steel has a heat retention, so it rises up to 60 degrees. And then from that point, the simulation starts. So if you move into the next slide. Yeah, so this is what the evaporation rate looks like. So I have 3 different system pressure, some kilopascal to 12 kilopascal. The idea is to show that as the pressure goes down, the evaporation rate goes up, which is like the simple physics. But one important thing here is that the evaporation rate goes up and then it goes down. So what happens is that I haven't considered in the design, they have a fan which removes the humidity and moves it into the freshwater side, which I did not consider. So as the humidity increases, the evaporation rate would slow down, which is reflected in these results. So
quick question about the color axis. I want to understand your animation better. What is the color axis there?
So it's the water content on the cylinder. As the water is evaporating, red is like having more water and the blue is like having less amount of water. So as the evaporation is occurring over time, the amount of water on the cylinder is decreasing.
Okay, got it. Yeah.
And it's for the 7 kilopascal, it's 70 millibar, 7 kilopascal. Okay. So the water production per day, if I accumulate all this over integrated over day per meter square, it's about 16 kg, 16 kilogram of water, which is about 16 liter. So if we move into the next slide, we will see the temperature profile inside the cylinder.
No, sorry, a quick question. When you say per day, are you assuming 4 hours of sunlight, 6 hours of sunlight? Is it, or it's actually 24 hours?
No, so I'm assuming 12 hours of sunlight, and then 12 hours of like night.
Got it. Okay, perfect. Yeah, go ahead. Yeah.
So if it's the temperature profile with time, with respect to time. So what's happening is that as the evaporation occurs, the temperature, there's a dip in temperature profile which happens due to the evaporative cooling. I mean, as the water evaporates, it has a cooling effect into the entire system, which keeps the temperature from rising suddenly. And as the evaporation rate slows down due to the moisture content, the temperature will rise down. So what I'm trying to show here is that there exists an operating point where you want your thing to operate. I mean, if the temperature drops down too low, the evaporation rate itself would drop down, because at lower temperature, the evaporation rate slows down. So you can figure out the operating point and the humidity that you want, because removing entire humidity or like keeping the temperature too high would come at a cost. So if we move into the next slide, I would hand over to Cedric to talk about the passive radiative cooler for condensation and so on.
So in addition to looking at the simulations of the evaporation chamber, which was just shown, we look into incorporating 2 different other technologies in our innovation. And that's the first one here I'll talk about is the passive radiative cooler. The passive radiative cooler is a material that you can see up in the upper right hand here, which is essentially just glass microbeads sandwiched between 2 layers of plastic. What it does is it emits radiation through the atmospheric transparency band. It allows it to cool a surface below ambient temperature. And so we want to apply this onto the condenser surface and also the freshwater basin. And so as I mentioned before, we want to have that freshwater basin at a lower temperature than the saltwater basin. And that's because freshwater evaporates at a lower temperature than the saltwater, so we don't want to have any back evaporation. So that's where this delta T comes in. We want that to be about 10 degrees Celsius. So we can look at an energy balance for the condenser. We have the energy in, which is essentially the feed water or the mass of condensed water here, times the latent heat of vaporization, which is delta H vape, plus the specific heat of water times the temperature difference that we want to maintain. We can say that the mass flow rate is essentially the evaporation rate times the area of the evaporator. And then we can look at the energy out, which is the power of the radiative cooler, P cooler, times the area of the condenser. From the paper that does an analysis of this passive radiative cooler, they found that the cooling power is about 93 watts per meter squared at noon, which is the low estimate. So it's integrated over the daytime, it's about 110 watts per meter squared. But we'll just stick with this low estimate of 93 watts per meter squared. So if you set these 2 equations equal to each other, we can solve for the ratio of the condenser and the evaporator area that we need to achieve to get an energy balance at a steady state. And what we find is that the condenser has to be about 13.7% as large as the evaporator. And that's really a positive result that we found, because we want to have a large evaporation area and a low area footprint for our condenser. So only about 14% is a good result. So moving on to the next technology we also want to incorporate in our design is a wicking material. And so what the wicking material does is we can basically coat the sidewalls of the evaporation chamber with the wicking material, which effectively increases the evaporation area of the design without having to build new structures or take up more of a footprint. So the simulation here that is shown is a simulation with simple paper as a wick, which is not something we would use, but just because the properties were readily available is why we simulated this. What you can see as the time increases, the water is drawn up the wick, which increases the evaporation area. So if you look at the evaporation area without the wick, just on the surface of the water, you can calculate that as pi r squared. If you add the wick around the sidewalls of the evaporation chamber, you can get pi r squared plus 2 pi r h, where h is the height of that wicking material. So you can actually drastically increase the evaporation area just by adding this wicking material around the outside. So you can see if with the chamber that we simulated, if you have an H of 10 centimeters, your area increases by about 50%. And likewise, with 20 centimeters of wicking material, you can increase the evaporation area to about double. The wicking material also can serve as an insulating material around the sidewalls of the evaporator, so you have an improved benefit there as well. And then we want to look at using Zorb cloth, which was used in other papers on wicking solar desalinization systems.
I had a quick question. This is a really interesting concept. What about residue that's left within this wicking material as the water evaporates?
That's a really good question. So I read a paper about the Zorb cloth where they did they use this as a wicking material to draw seawater. It's actually a floating solar desalinization system that floats on the ocean surface. And the Zorb cloth actually wicks up water and relieves the salt and the other particles beneath. So it doesn't really wick up the salt, it just wicks up the water. So that would be an issue, is that it would leave the salt in the basin.
Okay.
Yeah, so eventually the salt would build up in the basin. And that's something that we would have to do with our design, is like every day you have to waste the water out of the saltwater basin and put so-called fresh salt water in the basin.
Mm-hmm. Okay, go ahead.
Yeah, that's something that would have to be done either manually each year or so. But the Zorb cloth is something that has much higher wicking ability than simple paper. And it's much more durable as well. And it's also commercially available at pretty cheap. It's only about $10 per yard. So that's something that we would like to incorporate in our design.
So due to COVID, we weren't actually able to build or design our apparatus, but this is a diagram taken from an experiment done using a similar design. So ours would essentially consist of the solar collector, your fan, your passive radiative cooler / condenser, and then your seawater, brine, and freshwater units. Of course, you're gonna have your data logging tools and your ambient measuring apparatus to kind of control the external factors. Essentially, this left-hand column right here acts as your evaporator column, where the solar rays heats up the seawater and the vapor waters are then processed through, where the fan then mass transfers that vapor to the cooling / condenser unit. And then from there, it is then flown back into the freshwater unit. Again, our design was based on making it as cheap as possible and making it as commercially applicable. So we went for using the most cost-effective materials, and Cedric can kind of go over the specific materials and costs.
Yeah, so we wanted to make our system portable and also available to people that don't have electricity. So we need a fan to actually push the water vapor from the evaporating chamber into the condensing chamber, and we wanted to make that solar powered, so we incorporated using a solar panel to actually power the fan that drives that mass transfer. But to look at some of the materials that we'll need here is first vacuum chambers. So we proposed to make that out of stainless steel. The cost of is about $100 for the stainless steel, and a glass cover to allow the solar radiation to enter the evaporation chamber is about $40.
Quick question, Cedric. Why wouldn't you make a vacuum chamber out of glass? Because windows people make in large quantities, like vacuum windows and things. I mean, like insulating windows have vacuum in them, right? Sometimes, or nitrogen.
Yeah, we could make the entire evaporation chamber out of glass.
Is it too heavy or something?
More expensive to do it that way, so that's kind of why we stuck with steel. And that would just be like the sidewalls. The top obviously would be glass, and the glass cover would also be inclined at an angle similar to the sun angle, so allow the collection of the most solar radiation.
Okay, go ahead. Yeah.
So then the other components are obviously tubing to connect, so to allow us to flow the water down the height and create that natural vacuum, as well as connecting the evaporation in the condensing chamber. And so that was about $80 for the tubing, some valves to stop the flow and to allow the natural vacuum to be created was about $30 for the 3 valves that would be needed. fan was about $20. The solar panel to power that fan was about $35. The cost of the passive radiative cooler is unknown. It wasn't really talked about in the paper that we read about this new material, because it's a relatively new material that they've designed. But they did note that it can be mass produced at a rate of 5 meters per minute, which is pretty significant. And notably, we wouldn't need very much of it, depending on the size of the system, but like probably less than 5 meters for a residential system. And then for the wicking material, as I mentioned before, it's about $10 per yard. And we only need about 2.5 yards to cover the inside sidewalls of the evaporation chamber. So we estimate our total cost for the system is about $340, and that would be for like a prototyping on the system. If this system were to be mass produced, it would probably be lower than that. Then you'd have to kind of factor in some other costs as well. But I would say about $300 would be the cost of the system.
So if we look at the benefits, some of the benefits of using this system with the solar steel is that first of all, let's think that a family of 3 needs 20 gallons of fresh water every day. So for that, with the evaporation rate that we have, it has to be a 4.7 meters square of a total evaporation area, which would mean the system would be at least 4 meters square, which is not that big. It's a 2 meter by 2 meter, which is a 6 foot by 6 foot thing. And so we can place it on the roof of a house of a small family, and still they would have like other spaces to do like things on the roof. And the total cost of water per day will be about 1 cent or so. That is assuming that the operating cost is $1 per ton of water, which is not big because we don't have lots of moving parts and everything. The only maintenance that has to be done, it has to be the valves and the fan, which will at some point become corroded with salts and everything. And if we look at in a comparison of like how much the water from other sources cost, we can see that it varies from location to location, from 34 cents to about $2. But if you look at like locations, you will see that in drier areas the cost of water is higher, so we can so this solar steel can be a solution for like drier areas about Africa or like dry Texas, somewhere around. So that is it for our presentation. So if you have any questions, we'll be happy to.
So that was also very good. By the way, we went way over even with just not having a team. So I have to be more careful next time. Well, thank you. I think everybody did a fantastic job, and I'm very excited to see the last presentation. I would just add, for the last presentation, we will have several external members of the audience, so we definitely need to keep in mind, keep on time, and make sure you do your best job. In fact, I'll ask them to give some grading as well, which I will take into account. Okay, with that, we'll end here. Everyone have a good weekend, and we'll see you next week. Take care.
Thank you.
Bye.